Hello everyone. In this video we are going to start with our second chapter, which will be about how to design for our vertical elements using CSI ETABS. Now in our previous chapter we have learned how to design for our different slab systems, how to determine which slab system we should use, and how to determine the thickness of our slab as well as the structural components of our slab. Now in this lecture, what we are going to do is we are going to talk about how are we supposed to distribute our vertical elements throughout our plan. How does a civil engineer or a structural engineer look or view a plan, and how does an architect view a plan or this plan, as well as what dimensions are we supposed to use for our shear walls and our vertical systems as a whole, and the steps needed to design a building. What steps are we supposed to take to design a building? Now we are going to start with our last point, which is what steps does a civil engineer go through in order to design a building? The first step is you should determine the type of slab that we are going to use along with its thickness and its structural component, which we learned how to do in our previous chapter, which was CSI safe for different types of slabs. Now, the second step is we need to design for our vertical elements using ETABS, and this is what we will be learning in this course. We're going to be learning how to distribute our vertical elements and how to design for them using ETABS. Now, the design or the steps you take in order to design your vertical elements is very similar to the steps it takes to design our slab system. You have to prepare your plan, prepare an analytical plan, import it into SAFE. Then you have to check for serviceability condition. In our SAFE course, we used to check for deflection and punching shear. However, here we are going to be checking for sway and drift. If our sway and drift are okay, then we can move on to design for our vertical elements. Now, the final step is we are going to take the data that we got from CSI ETABS and we are going to import it into CSI Safe to design for our foundation. So our three main steps are CSI Safes for our slab system, then we are going to CSI ETABS for our vertical elements, and finally CSI Safe again for our foundation system. Now, what we have in front of us here is a architectural plan. This we are not used to such an architectural plan. Usually this is what an architect sends when you are working on a multi-story project. And the way we read this plan is like architects usually send these plans with the following format. You start from the higher floors, your roof floor, for example, here, and then you move on to your typical floors, and finally you have your ground floor and your basement floor if you have a basement floor. So you have your plan views here, you have your section view and your elevations. So if you notice one thing here, it is that our architect already distributed our vertical elements, and we realize that our vertical elements are mainly our columns. However, this design here is prohibited for high seismic zone areas because this design does not contain any shear walls. Your only support system against lateral loads is your columns. So what we are going to do here is we are going to add shear walls along our system in order to make this structure able to resist earthquake loads. Now, the reason our architect basically distributed only columns without any shear walls is maybe the way he looks into a plan. So if we try and see what's the point of view when an architect looks into a plan and what's the point of view of a civil engineer when he looks into a plan, we can understand a bit more of the design perspective that goes into play. So when an architect looks into a plan, what he does is, let's say he takes a cut here at the midpoint or mid-span, and he looks downwards. Because what an architect cares about is what is he placing on your slab, like what vertical or what structural components are coming out of the slab, and how is he supposed to optimize his design, or how is he supposed to make the looks more appealing according to the distribution of his structural elements. And usually he distributes the structural components such as the columns based on the architectural design and the looks of your floors. Now, the civil engineer, the way a structural engineer looks into a plan is that he takes a cut and he looks upwards, because what a structural engineer cares about is this slab and how is he supposed to support it. What is going to support this slab? He does not care about what's coming out of the slab. He cares about what is going to hold this slab. And this is why when we draw our vertical elements, we are going to see this later on when we start distributing our vertical elements. Let's say we want to distribute vertical elements for our roof. What we do is we move to the lower floor or the floor beneath it, and we check the vertical or the vertical elements there, and then we move on to represent this design into our roof floor. Now, this is basically the difference between how an architect looks into a plan and how does a structural engineer look into a plan. Now, when it comes to your slab limit or other structural components such as slab limits and voids, these are floor dependent, so you do not have to move into the lower floor in order to be able to draw them. So you can draw them floor by floor. Now, when it comes to your beams, we know that our beams are embedded within our partition walls. So in order to draw your beams, you also have to move to the floor beneath the floor you're working with in order to be able to draw your beams. Now, the next point here is we need to maintain consistency within our layouts or our different floors. We need to make sure that the distance between each layout is equal and they are all on the same level. This way we are representing or we are showing that all of our floors are right on top of each other. Now, how can we do that? In order to do that, we need to define a reference point. Now, what is a reference point? Now, a reference point, we talked about it before. It is a point that is located somewhere that does not change throughout the whole duration of the project. We said that the intersection of two axes is a perfect location for a reference point because your axes do not change in location throughout the whole duration of the project. Now, the reference point I'm going to choose is the intersection of these two axes. What I'm going to do is I'm going to draw a line from here up. Then I'm going to select this line, create an offset of 50, offset 50 here to here, and then this to this, this to this, and then this to this. Then what I'm going to do is I'm going to select all of my plan. I'm going to move it from the intersection to this point here. This way I can make sure that all of my plans are consistent or are symmetric, so that we can show that all the floors are right on top of each other and we can accurately distribute our vertical elements within our floors. So I'm going to move all of my plans and I'll be back when I'm done. Okay, so now that I am done with making all of my layouts symmetric, I have all of them on the same level and at equal distances from one another, I can move on to my next step, which will be defining my layers. So just like we used to do before, layer properties, I have already defined my layers. You have your beam, your columns, your slab limits, you have your voids and your walls. These are the colors that I chose: green for beams, magenta for columns, blue for slab limits, red for voids, and a magenta for our walls. I changed the line weight so that we will be able to see our structural elements clearly within our plan. So now we can close this. We are going to start with drawing our slab limit. So let's start from our roof floor. Draw a polyline. From here, we're going to go up, follow the outer periphery of your wall, just like we used to do before with our slab system. Okay. Okay, I'm going to skip to the part where I'm done with drawing this and I'll be back. Okay, so now that I am done with drawing my slab limits, we can move on to our next part, which is distributing our vertical elements. Now, as we mentioned before, we want to distribute our vertical elements, we have to move to the floor, to the lower floors, which is this floor here. So now we want to distribute our vertical elements. We can see that this structure system is a cantilever column system, which means that our only vertical elements here are our columns. Now, this, as we mentioned before, is prohibited in high seismic zone areas. Now, how can we design a structural system that can resist earthquake loads? What are the criteria required in order to do so? Now, the first criteria is we need to add vertical elements such as our columns, which are already distributed by our architect, and shear walls that we are going to distribute along our system. Now, where are we going to distribute or to place our shear walls? Of course, the first thing is we do not need to interfere with the architectural design. So we cannot place a shear wall in the middle of a living room, for example. Now, usually we place shear walls along the outer periphery of our system. Now, why is that? This is to give a big lever arm for our structural system as a whole. A lever arm is basically the distance between two forces, which are your compression and your tension. So if we want to take an example of that, usually if you want to rotate an object, you do not rotate an object from the center. You hold it from the edges and you rotate it. Now this is the same case here. The bigger the lever arm, the better the resisting force is, or the better the resistance is against earthquake loads or lateral loads in general. So this is the reason that we place our shear walls along the outer periphery of our system. Now, the second criteria is we have to try as much as possible to maintain symmetry within our plan. So let's say here I place a shear wall here, I have to place a shear wall here. Let's say I place a wall here, I have to place a wall here as well. And the same goes for the opposite side. So this is easy if your floor is fully symmetric. However, with the case of our floor is symmetric along the y direction, which means our right side is the same as our left side, but it is not symmetric along the x direction. Our upper side is not the same as our lower side. So we are going to see how we are going to deal with this later on. So these are basically the two criteria that we need to satisfy in order to design a system that can resist earthquake loads. Now, before we start distributing our shear walls, we have to discuss the dimensions of our shear walls. What are the dimensions that we are going to use? The preliminary dimensions. Now, there are three criteria that can help us determine the dimensions for our shear walls. Now, the first criteria follows the code. The code tells us that the minimum thickness for our shear wall has to be 0.25 meters, and the length has to be 5 times the wall thickness. So you have 0.25 by 1.25. However, there are some codes that require a minimum length of 1.5. So this is the first wall that we are going to draw. So let's draw a rectangle distance 0.25 by 1.5. Okay, this is the dimension of my first wall here. So this is the first criteria. Now when it comes to my second criteria is related to the height of the building. Now if you remember, when we used to work with cantilevers, the preliminary thickness of our wall was determined by taking the length of our cantilever and dividing it by 10. Now this is very similar in the case of our building. Your building, you can look at it as a cantilever because it's fixed from the bottom and it's free from the top. So if you want to find the dimension or the minimum length of your wall, what we can do is we can take the height of our building and divide it by 10. Now how can we find the height of our building? We can simply go to this view here and check the elevation, which is 18.5. So 18.5 divided by 10 is 1.85 meters. So let's draw a rectangle. Okay, here dimensions of 0.25, 1.85. Okay, let's delete this again, draw a rectangle. Okay, dimensions 0.25, 1.85. This is the second criteria for my wall dimensions. Now I have one final criteria, and before I move to it, I need to discuss an important point related to my wall's thickness. Now, if you use our common sense here, the loading as you move downwards along your building, the loading increases on your structural components. So let's say you're working with your ground floor, the loading on your structural components is higher than your roof, for example, because your ground floor is carrying your whole building. So what what are we supposed to do when it comes to that? How do we work with such an issue? Now what we usually do is every 3 to 4 floors, we try to increase the thickness of our shear wall by 5 centimeters. So let's take our case here. We have 8 floors. So the first 4 floors are going to have a dimension of 0.25 by let's say 1.85, and then your second 4 floors are going to have a dimension of 0.3 by 1.85. This is to make up for the increase in loading that is occurring at the lower floors. Now, one thing we can do here before we continue is delete these frames and our lines because we do not need them. Okay. Okay. Here, here, this, this, and this. Okay. Now we can move on to our last criteria and we are going to talk about it here. Okay, now usually some walls or many walls are uniformly reinforced, which means that they have equal spacing along a certain length. However, other walls have boundary zones. Now, what is a boundary zone? It is as if you have an embedded column within your wall. It is heavily reinforced. Now, why do we usually have boundary zones? Because boundary zone increases the flexural capacity of your wall. So if you have two walls of the same type and you include a boundary zone within one wall and you uniformly reinforce the other, the capacity of your first wall is going to be much higher than your second wall, and this is why we usually add boundary zones. Now, how can we find the dimensions of our boundary zones? Usually the dimensions are, according to our code, 0.15 to 0.3 times the length. However, we don't know the length yet. So what we can do is we can take the dimensions of our boundary zones to be the thickness by 2 times the thickness. So if you have a thickness of 0.3, your length or your boundary zone's length is going to be 0.6. So we have now 0.6 from the left and 0.6 from the right. Now, what is the length of the uniformly reinforced area? Now, we are going to take this as the preliminary dimension or the preliminary length we took before according to the code, which is 1.25. So we are going to have a 0.6 boundary zone here, 1.25 uniformly reinforced area here, and 0.6 boundary zone to your right. So this will make up for 2.45 meters length. So the third dimension here is going to be, or the dimension for my third criteria is going to be dimension 0.25 by 2.5. We are going to round it up to 2.5. Okay, so these are the three preliminary dimensions for my walls. We are going to see which one we are going to choose based on our structure necessity on the space that is available for us. Now this will be it for this lecture. In our next lecture we are going to start with the distribution of our vertical elements throughout our plan and trying to mirror it along the rest of the floors. So I'll see you in our next video.